Hi everyone, my name is Sarina Meyer and I'm representing the team IMS from the University of Stuttgart in Germany at the VoicePrivacy Challenge 2022. First of all, I'm going to assume that you are familiar with the VoicePrivacy Challenge, so I'm not going to explain the goal of this challenge, its framework or its evaluation any further. Let's start with our idea. We saw some problems with the challenge baselines. The primary baselines B1A and B use the pitch and bottleneck features of the original audio for synthesize their anonymized ones. The problem of this is that pitch and bottleneck features contain some information about speakers that can lead to identity leakage. The secondary baseline uses a simple signal processing method, which is not really robust against neural attackers that are used in this challenge. Our approach is based on the pipeline of the primary baselines, but we use a phonetic speech recognition model. This means that we reduce the speech to its linguistic content in form of phones. This is good because this is designed for an optimal interaction with the TTS. In the TTS itself, we don't have to phonemize the text anymore, which means that this whole pipeline is less error prone. We use a speaker embedding anonymization method using a GAN model. This generates us artificial, so non-existent voices that are still natural-like. And finally, we have a multi-speaker speech synthesis model that is optimized to produce distinctive voices based on its speaker embedding. You should note that we are not using the original pitch for the synthesis, but instead we are estimating the pitch in a smart way. Why we are doing this, I'm going to go back to that later on. So here you see our speaker anonymization pipeline. It looks very similar to the pipeline of the primary baselines. So it uses the original speech to recognize the linguistic content in it with an ASR model. But instead of using the bottleneck features in the ASR model, we use directly the output in form of phone sequences. And as in the baselines, we are extracting the speaker embeddings and using the original speaker embedding for the anonymization. But our anonymization is based on a GAN model that is generating a new anonymized speaker embedding that does not exist before. And using this anonymized speaker embedding and the phone sequence that was recognized by the ASR model, we are resynthesizing the audio to produce an anonymized speech recording that still contains the linguistic content and so on of the original audio, but where you cannot identify the original speaker anymore. Let's go through the components one by one. So first of all, we have a speech recognition model that is using a hybrid CTC attention architecture with a conformer encoder and a transformer decoder. It is implemented in the ASP.NET 2 toolkit. The output of this model is phone sequences. So this is rather unusual for ASR model. Usually you would have text as output of the ASR model and not phones. But we found that phones are actually better suited for this task because this means that the synthesis model does not have to phonemize the text anymore, which also means that we have a less error-prone step in our pipeline. And we also found that phone sequences are more robust against errors in our ASR model. So because every error that is made during the speech recognition at the beginning of the pipeline is propagated through all of it and is reflected in the speech synthesis output. And we found that phone sequences reduces this error. One problem of these phone sequences is that we need training data that is phonemized, and usually our training data is not. So we are using the IMS toolkit, which is a speech synthesis toolkit, to transcribe the training data for the speech recognition model. The speech recognition model is trained as follows. It is first trained on the LibreTTS data. The resulting model is then used to label the VoxelLab Corpora 1 and 2. And then the model is fine-tuned on this labeled VoxelLab data together with the LibreTTS data. This whole process is repeated 2 times and led to the best and most robust and less error-prone ASR model. Our second component is the GAN-based speaker anonymization. We are using 2 types of speaker embeddings, X-vectors as in the baseline systems and eCapacitian embeddings. We found that these 2 types contain complementary information about a voice, and by concatenating them in our speaker anonymization pipeline, we are having more detailed information about the voice. So the concatenation results in vectors that span 704 dimensions and are extracted with SpeechBrain. We are training a Wasserstein generative and adversarial network with quadratic transport cost to generate new artificial speaker embeddings. So this architecture is optimized towards convergence because GANs usually have the problem of being difficult to train to convergence. And also this architecture reduces the problem of mode collapse that is typical to GAN models. We have a generator that uses noise vectors to transform them into 704-dimensional vectors, so the same dimensions as our original speaker embeddings. And a critic, which is basically like the discriminator of a Wasserstein GAN. And this critic distinguishes between real and fake data distributions. So this is different in a Wasserstein GAN than an original GAN, because we are not distinguishing whether a sample is real or fake, but only whether the distributions are real or fake. And obviously our generator wants to generate vectors that are more close to the real data distribution so that the critic cannot distinguish them anymore. During training, we use utterance level speaker embeddings. So this means that we are extracting speaker embedding for each utterance and use this for the training. But during inference, we generate only one embedding per speaker and dataset, so that each speaker has the same voice in the new dataset. One exception is the training data for the evaluation models. There we use the utterance level speaker embeddings as defined in the evaluation framework. The final module is our speech synthesis model. It uses fast speech 2 synthesis to translate from phones to spectrograms and a hi-fi GAN vocoder to translate from spectrograms to waveforms. Everything is implemented in the IMS Toucan toolkit mentioned before. And this toolkit converts the phone input first into articulatory features before this is fed into the fast speech 2 synthesis. The pitch and energy estimators are based on fast speech 2 and fast pitch. And we train the model conditioned on concatenated speaker embeddings in order to produce actually voices that are different depending on the speaker embedding. Let's jump directly to the results of our method. So in the primary evaluation, the first metric is the privacy metric, assessed by using an ISV attacker that is actually pretty strong because it is retrained on the training data that is anonymized with the same pipeline as I showed you before. And because this attacker is so strong, the baseline models actually don't have a really good performance. So they have all a pretty low equal error rate. And the lower the equal error rate is, the easier it is for the attacker to distinguish whether an utterance came from a certain speaker or not. But our method produces anonymized data, which makes it more difficult for the attacker. So we see that we have almost perfect privacy with our method. So we have an equal error rate that is close to 50%, which means that the attacker makes basically random decisions between whether this utterance actually belongs to the speaker or not. The second primary evaluation metric is the speech recognition metric. Here a lower score is better because we want to reduce the word error rate. And here our scores are more closer to those in the baseline, but nonetheless our method has the best word error rate scores. It is even better than for the original data that you see on the left. And this is due to the VCTK dataset. The VCTK dataset is a challenging dataset because it contains different English accents, which is obviously problematic for speech recognition. But here we could actually, with our anonymization method, reduce the word error rate for the VCTK data from 12.8 to a 7.8 word error rate. This means that we are losing the information about the accent of a speaker, which is still also a speaker-specific information, and that our data is actually more intelligible than it was originally. In the secondary evaluation, we also have two metrics. So first, the pitch correlation metric, which measures how much the pitch sequence of the anonymized data correlates to the original pitch. So how much the intonation is kept basically during the anonymization. And here we have pretty low scores. So we have by far the lowest pitch correlation scores because we are not using this pitch information, right? But still we are meeting the threshold of 0.3 of pitch correlation for all data sets, which is a requirement for this challenge. The second metric is gain of voice distinctiveness, which measures how much of the ability to distinguish between voices in the original data is kept during the anonymization. And here a score of 0 or close to 0 means that it has the same voice distinctiveness as it originally had. And the lower the score is, the more it means that the voices are more similar and cannot be distinguished anymore. And here again we see that our method outperforms the baseline models, especially the neural ones, which are pretty bad in this regard. And we see that our method has a distinctiveness that is very, very similar to the one of the original data. Okay, let's go back to the low correlation scores that we got for pitch. So it is obvious why we have those low correlation scores, because we are not using the original pitch sequences in any way in our synthesis. And this is actually a deliberate choice that we made, because we saw that pitch still contains some information about the speaker that makes them identifiable. And we saw also that it is best for our system to have no information at all about the original prosody of the speech, in order to make it more privacy preserving. But wait a minute, no information? So would this mean that we are losing the information about when it is a question and when it is a statement and so on? Well, actually, this is not true. So let's rephrase this. It is actually best for our system to have no information about specific values of the original prosody. So to have no information about the specific pitch values and so on. Because we are using some prosodic information in our transcriptions. Our ASR model is trained on LibriTTS for a purpose. LibriTTS, in contrast to LibriSpeech, contains punctuation. So this means by training our ASR model on it, the output of the ASR actually contains punctuation. And also the context and the word order of the phonemized output gives some hints about the intonation. And these 3 points, punctuation, context, and word order, are actually enough for our energy and pitch estimation methods so that they can basically estimate more or less the original intonation. Okay, let's conclude this presentation. So our system is a speaker anonymization pipeline with phonetic ASR transcriptions, GAN-generated artificial but still natural-like anonymous speaker embeddings, and a multi-speaker TTS that uses a smart pitch estimation instead of using the original pitch values. And we saw that we highly outperform all the baselines in 3 of 4 metrics. So we saw that we are achieving almost perfect privacy even against a strong attacker as used in this challenge. We have a better intelligibility than all the baselines and even better than the original VCTK data. And we produce utterances of basically the same voice distinctiveness as the original data had. And we deliberately not keep the pitch information in our synthesis because we want to reduce the identity leakage coming from it. But nonetheless, we are producing anonymized recordings that are relatively matching in the intonation to the original ones. Okay, thank you for listening to my presentation. If you have any questions, don't hesitate to ask me. And here are all my references.